Okay, Zainab.
A chemical change would no chemical reaction would be a chemical change between elements, and it's normally not reversible.
Yeah, that's a good definition. Does anyone else want to try?
A reaction in which reactants react with each other and form products.
Yeah, and the product is different from the reactant, right? Okay. So that's a chemical reaction. Both Zainab and Nabil are right. Okay, so a chemical reaction is a reaction between a chemical reaction is when two elements bond with each other to give us a product which has different chemical and physical properties, different compared to the reactants. Okay, so whenever we have a chemical reaction, some chemical reactions are spontaneous and some need to be given a boost of energy to get started. Okay, so even the ones that are spontaneous, for we it might seem to us that they are spontaneous, but like they're happening on their own, but they too need a kickstart. Nothing happens on its own. Okay, so before I get into this, I want to introduce you to two new terms: enthalpy and entropy. So I'm going to talk about enthalpy first. So enthalpy, if I just give you a definition, is an increase or decrease of energy during a chemical reaction. So um, so this is after a chemical reaction or during a chemical reaction, there can be an increase or decrease of energy. And what do I mean by energy? The measurable amount of energy, the measurable way of the measurable the way we can measure the energy is temperature, right? So there can be an increase or decrease of temperature during a chemical reaction. But of course, there are other energy changes going on, but where we can only measure heat. Okay, so let me explain what enthalpy is. So first of all, we know that every chemical bond has chemical potential energy stored in it, right? So molecules with less of this energy will be more stable than larger molecules which have more bonds and so more chemical potential energy. So I have nitrogen here, right? So this is um, the nitrogen. Okay, so a molecule of nitrogen, it has three bonds. It has a triple bond. Okay, so three bonds here, and the bonds over here are four. Okay, so there are eight bonds here. Okay, eight bonds here, three bonds here. Obviously, this is going to have more chemical potential energy because every bond has chemical potential energy. So this molecule is more stable and this molecule is less stable. And now focus on the word potential. So potential is the promise of work going to be done in the future. Okay? So that means it has a potential to do something. And that is why hydrocarbons are so flammable. Okay? So large molecules like this have more chemical potential energy stored in them. Okay? Okay, so now moving on to enthalpy. Okay, so so first of all, um, I told you that enthalpy could be an increase or decrease of energy or temperature during a reaction, right? So a reaction in which the temperature is increasing is going to be called a exothermic reaction. Okay, so exo means exo rhymes with exit. Okay, it's also derived from exit. Okay, so exothermic, therm means heat, so heat is exiting, heat is leaving the reaction. Okay, so if I treat this as a golf ball game. Okay, so I have a golf ball here. Okay, and with every rise or fall, I need to provide or remove energy. Okay, so let's think of chemical potential energy as gravitational potential energy for now. Okay, so this gravity is moving downwards, right? And this ball, we want it to get into this hole. Once it gets into this hole, that means we have our product. Okay, so it's moving against gravity, right? So there's going to be less energy, and we're gonna give in energy because obviously we need to give that ball a push to move it up. It's not gonna move up on its own. It would rather go towards gravity. Like it's gonna um, it's gonna move in the direction where force is applied, right? So we have to apply force greater than the force of gravity pushing it downwards to get it up this hill. So I added energy. So I added energy here. What's the R? Okay, so I added energy here. Okay, and now it's gonna move down on its own, right? So when it's moving down on its own, I told you to think of this as gravitational potential energy. So we have gravitational potential energy here, and as it's going down, it turns into kinetic energy, right? So heat energy is, or heat is getting lost. So energy is getting lost, and then it comes into the hole, and so we have our product. So this is how exothermic reactions work. Okay, and I also don't want you to get confused when they compare exo and endothermic reaction. Exothermic reaction, I want you to remember one thing: the energy supplied is less in comparison to the energy given out. Okay, not in comparison to anything else. This energy given in is less compared to the energy given out. That's why the rise is smaller. Okay, so this is an exothermic reaction. That means we will feel the temperature rise, and I'll also give you another example as we move on. Okay, so now that I've given you like a visual example, sort of, let's like graph what we just learned. Okay, so I'm gonna draw a energy profile or an energy diagram. Okay, so this is basically a graph, okay, where the x-axis, okay, so the x-axis is time, and over here I have energy, y-axis. And for now, I want you to think of it as potential energy, okay? So, so if this is the energy, the potential energy for my reactants, so I'm going to write a R for my reactants, okay? And this was the potential energy of my product, right? Okay. So the products over here, I mean the reactants over here, the molecules over here, the substances over here are going to have more potential energy because like they're higher up, and once they become products, they don't have that much of a potential energy, right? So the reason why I'm mentioning potential energy and I'm making you visualize this in the form of gravitational potential energy is because it is sort of like that. So this is chemical potential energy, okay? So these reactants have more potential energy, and that's why they reacted. And the products are products for a reason. They don't have that much of potential energy, okay? So as the molecules are gonna go from reactant to product, energy is going to be released, right?
Sundus, I'm sorry to interrupt you. Assalamu alaikum wa rahmatullahi wa barakatuhu. I just wanted to add a little point here, that yes, you're using a good analogy of potential energy with these. I mean, in this particular scenario. But the thing is that, remember, all the substances in this universe, they want to be stable. Okay, so the concept of stability should be introduced at this point. Substances are trying to be stable. So just like when you are on a fourth floor, you are less stable as compared to when you are on the ground floor. What do I mean by stability? What do you understand by stability? Who will tell me what stability means? The word stability, both in physics as well as chemistry. Yes, Maruj. I unmuted
It
you. Yes.
it means that equal balance.
Stability means equivalence? No. Okay. Zena, okay. Let me give Muhammad a chance. Okay, Muhammad 32.
It means to be more unreactive.
No, I said a definition that will be applicable both in physics as well as chemistry. Yes, Momina. Yes, Momina. Momina, I unmuted you. Okay. Zainab, I unmuted you.
Yeah.
Yes.
Can you repeat it, please?
I asked what does stability mean?
Stability would mean like to do stability would be the kind of like a phase in which you try to avoid any change.
Yes. Yes. Okay. So yeah, yes. Stability means to stay the same, stay what you are. Okay. Everybody, what what do we mean when we say, it will take me some time to stabilize? What does that mean when we use it in a daily language? When we use this word in daily language, it means stabilize means to be comfortable with your surroundings, and that you have an assurity that nothing will change, that things will stay the way they are. Like, nobody wants to be unstable, nobody wants to be insecure, not knowing what would happen tomorrow, or not, like, we like to be secure, we like to be stable. So substances and molecules are the same way. They want to be on an energy level where they know that they will be stable. So all these reactions and electron losing and gaining and everything, all this is in a struggle to achieve that stability. Okay, so when the energy level of molecules is higher, yes, Sundus used a good analogy. It's like when your potential energy is higher, like when you are on on a higher floor, like when you are on the fifth floor. Why is it that when you are on a fifth floor you are more stable than when you are on a ground floor? Now look at it this way: you cannot stay on the fifth floor forever. You will come on the ground sometime, right? You cannot stay on the fifth floor forever, even if you are living on the fifth floor. Okay, and there is always danger of you falling down when that opportunity arises. So you will when you are on the ground, you will not need walls around you to make you feel safe. But when you are on the fifth floor, you need those walls to make you feel safe, right? Why? Because you are unstable on the fifth floor, and you are the most stable when you are on the ground floor. So it's the same way. So when the molecules have a higher potential, or when the molecules have greater you can say energy in their bonds, so they are unstable, and they are waiting for that chance to turn into molecules which are more stable and therefore at a lower energy level, or you can say on a lower floor. So people living on the first floor are more stable as compared to people living on, let's suppose, 11th floor. I hope you got my point. So these are just analogies, but yes, you got the point, right? So molecules will try to get from unstable to more stable. Okay. Okay, Sundus. So I added what I wanted to add. Continue.
Yeah, so they'll basically like try to fall from the higher level like to the lower level, okay? But so they're gonna want to fall like from the higher level to the lower level, but they wouldn't just do it like that, okay? So basically what happens is that if I take like the combustion of hydrogen and oxygen, uh, hydrogen is like bonded like this, right? So they're 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 like happy, okay, in this state, like sort of. I know like the products are more like stable, but um so this is just an analogy, okay? Again, so it's they're just like fine in this way, okay, and so is the oxygen, okay?
Fine meaning stable. Fine meaning stable. Okay. They're fine meaning that they're stable. Yes.
Yeah. So okay, so basically there are many hydrogens, okay, in the atmosphere, okay, and I'm talking about the combustion of hydrogen, and so combustion is the reaction with oxygen, right? So now I will have to provide it heat to break the bonds, because as I'm going to provide heat, that is when they're going to start moving faster, right? So the kinetic kinetic theory, right? So when as I'm going to start adding heat, that's when they're going to start moving faster and they're going to start getting uncomfortable, okay? So their potential energy is going to rise, okay? So they're getting more uncomfortable, okay, and it takes them quite a while to like reach that level where their bonds will then be broken. So they're moving faster and faster and faster until a time comes when their bonds are broken. So their bonds are broken and they have to go pair up with someone new, and so water is formed, okay? So this is the combustion of hydrogen, okay? So the product is going to be water, okay? So we needed to add a bit of energy, okay, just to like start the reaction, and then it just falls down to its more stable form, okay? So the rest of the reaction just takes place automatically. You just have to like give it the start, and then the rest is easy, okay? So you know they have to climb uphill, but falling down is going to be obviously easy. So again, just think of it as potential energy, okay? So I told you we had to add energy, right? So we added energy, okay, just a bit, and but then the energy given out was way greater than the one we added. Can you see the length, right? So this will be obviously greater than this one, the energy added. So this is a exothermic reaction. I can say that this is a exothermic reaction, okay? Because I can measure the activation energy using the uh, um, y-axis, okay? So this is the activation energy, and then this is the energy that was so this is the enthalpy. This is the energy released, right? So this was the enthalpy, or this was the energy released, okay? So can you see that the activation energy is way smaller than the energy released? So this is what I mean by an exothermic reaction. Heat leaves the substance. Now
Okay,
the
so okay, so this
yeah,
this enthalpy, this is the net energy released. Okay,
oh
use the word net, because
yeah,
the actual energy released will be all the way from the top of the activation energy all the way till, you know, your pink line, you know, which you
yeah,
have marked as P.
yeah. I'm
Yes,
sorry.
that
That
will be
was
the
just
actual energy released, but this enthalpy would be the net energy released. Okay,
yeah, that was a mistake. Thank you for correcting me.
no, that's fine.
Okay, so where was that? Okay, so so this is what I mean by exothermic reaction. More energy is like leaving the reaction, okay? But then the common misconception is that why do exothermic reactions feel warmer? So this is why they feel warmer, because your hand is going to be experiencing this heat. So even though the stability of the product has decreased, I mean, has no, sorry. So the product has become more stable, so the stability has increased. You're going to be feeling the heat. You're going to be feeling the aftermath of the reaction. That's why it's going to feel warmer. So exothermic reactions feel warmer.
Okay,
Okay.
so this also I would like you to correct your water molecule that you have made with the green marker.
Oh my God, I'm
Oxygen
so
addition.
sorry.
That's fine. That's fine. Okay, Maruj wants to say something. Yes, yes, Maruj.
Which bond does these contains HH bond?
HH.
These HH bond, which bond are these?
These are covalent bonds.
Maruj, it's a covalent bond. Did that satisfy your question, or were you trying to ask something else?
Yes, that was a question. I was confused about the bonds.
Okay, can you tell me what covalent bond is? I just want to make sure that you're clear about this.
Yes, or when they both share their electrons.
Yes, both are trying to gain stability, and so both of them, so none of them is ready to give away. Both of them want to gain, and so they share. Okay.
Okay.
Yes. Okay. Nabil, your hand was raised, but okay. Okay, move on. Sundus.
Okay, so now another sort of reaction is endothermic reaction, and as you would have probably already guessed, it takes in more energy than it gives out. Okay, so the same analogy for the endothermic reaction. Okay, but this time we have to give the ball more energy, and then it's going to release less energy going down to this hole. So this is our golf ball. You have to give it a lot of energy. So a lot of energy being taken in, okay? And then it just has to go down this small hill. Okay, so it was a big rise, but the descent is lower. Is I mean less steep. Okay, so um, less energy is given out. And we have our product formed. Okay, so an example of this would be like nitrogen, and nitrogen combusting and oxygen, so giving us nitrogen monoxide. Okay, and that in itself, so nitrogen monoxide is less stable than nitrogen and oxygen, and I'll tell you how. Okay, so basically, first of all, I want you to just get cleared with the term. So endothermic, more energy in, less energy out. Okay, so now I'm going to graph this just like we did for the exothermic reaction. Okay, so same. So this is time, this is potential energy. Okay, um, and then we have our reactants over here.
Shouldn't we write just energy on the y-axis?
But yeah, but I'm just trying to make them visualize in the form of gravitation potential energy.
Yeah, okay, but you know, you also have to be careful that you don't want to be wrong scientifically.
Yeah, so
So,
this is just for the golf ball.
acha, okay. Okay, but you know, for chemical reactions, the y-axis should be energy. Okay.
Okay. I'll remove that.
Okay.
Okay, so this is okay, so that's this energy. This is a reactant, okay? So it's more stable, okay, than the product, okay? And we had to give in a lot of energy, okay? So this is the energy given in, okay? So so the energy given in is greater, but I can't make a straight line up from the reactant to the product, because if you remember, there was energy released, but it was less compared to the energy given in. So this is very important. You have to compare the energy given in with the energy given out. And
Also appreciate the fact that products are at a higher energy level as compared to reactants, and that shows that products are unstable as compared to reactants. So this reaction is not going to take place easily.
exactly, we have to give it a lot of energy.
Because molecules don't like to become unstable. So this will require a lot of input. Okay, another question. What does a spontaneous mean? Spontaneous. Just want to make sure that people know the meaning. Yes, Nabil. Oh, sorry. What did I do?
Suddenly, like, means explosively suddenly.
No, spontaneously. What does it spontaneously mean? Yes, Sarah.
Same at the same time.
No. See, it was a good thing I asked. Okay, Sidra wants to. Yes, Sidra.
It means to move without any external force.
Yeah, not necessarily move anything without any external force, meaning that, you know, that whatever process you're talking about, it's taking place on its own without any external push, without any sort of external force. Spontaneous. How many times have you come across this term spontaneous? For example, the definition of diffusion is what? Spontaneous movement of molecules, meaning that if you apply an external force, the movement is no longer spontaneous, the movement is no longer diffusion. So so this reaction where products are at a higher level than reactants is not going to be spontaneous. This is not a spontaneous reaction because molecules will never become unstable on their own. You will have to push them by, you know, supplying energy in the form of heat, electricity, or, you know, whatever. Okay, another thing I want to add here is that think of the activation energy. I used to use this analogy, and I'd love this analogy. Think of activation energy and think of energy as money. You know, energy is like money in our daily lives. We don't want to do things which are expensive, right? So endothermic reactions, meaning they require energy, meaning they require money. So they won't take place easily. Exothermic means profit. You know, people want to do business that gives them profit. So exothermic reaction, energy is released, meaning money is being produced. So easy reaction. The exothermic reactions will take place spontaneously. Spontaneous meaning on their own without any external force. Okay, so activation energy is that energy which you require to, it's like money that you have to invest before you start a business. For example, if a person wants to start a shop, now of course he is opening the shop because he wants to earn money. That's his ultimate goal, because he wants to have profit. But before he can have profit, he will have to buy a room, right? And for that he needs money. He will have to buy things to keep in the shop. For that he needs money. He will have to clean that room, take care of that room. He will have to hire somebody, you know, an employee, and he will have lots of other things to do. All of those things will require money. Okay, But once his shop is successful and it starts running, then he will start making profit. So reactions are the same way. Activation energy is that money that you have to put in first. The rest of the profit, when the shop eventually is successful and it produces energy, that is the profit, that the person starts getting once his shop is successful and everybody comes to and buys from him. So that's the ultimate energy which is released at the end. But before he does that, he requires that money to invest. And also appreciate that those businesses which require a lot of investment, like for example, if somebody wants to start open industries in different countries, well, that would require a lot of money, a lot of activation energy. Such reactions are not very common and they will not take place easily. So they are rare. So any reaction that has a lot of activation energy, meaning even if it is overall exothermic, because of that initial high activation energy, it will be difficult because it requires that initial input of energy. Okay. And reactions, the activation energy of which is less. Think of it as just starting a small business. Like for example, you start selling lemonade on a footpath. That requires nothing. You just have to have a few glasses, water, lemon, sugar, and that's it. And then you just stand there. So that is also a business. That's also a reaction, and you will get profit. So there will be an overall energy release, but investment was little. That means activation energy was little. So it's easier. Everybody can do it. So I hope that an analogy is useful or helpful. It helped me. Okay. So remember, reactions that have a lot of activation energy, and the analogy that Sundus is using is also helpful. So just think of it as a hill. Okay. Think of it as a hill. So the steeper the hill, and the peak of the hill is the activation energy. More steep the peak is, the difficult it would be for the ball. You will have to kick the ball with a lot of energy so that it can bypass, it can overcome that peak and then fall down and then come down. I hope I'm making sense. Okay, Sundus, continue.
Yeah, so in endothermic reactions, you have to give in more energy, but there was some energy given out. So I'm going to make sure that the energy that's given in is greater, but then this is the way the graph is going to be, because there was some energy given out even though that was less, right, compared to the energy given in. So this is the activation energy for this was was a lot. So the activation energy was going to be this whole thing, and the energy given out is going to be this part of the graph, right? So
yeah, be very careful about this. Activation energy is all the way from the reactants till that peak.
yeah,
This is your activation, because they ask this in MCQs so much. Activation, and especially in MCQs, activation energy is all the way from the reactants till the peak, because this is the energy you need to put in if you want this reaction to occur, to take place. You have to give this energy, and this energy is activation energy. Activation energy is the energy which you require to put in to make the reaction happen. Okay.
so okay, so I'm going to give you an example for endothermic reaction. So yeah, I forgot to give you the example for exothermic. Okay, so exothermic was like, so there's going to be a lot of release of energy, so like explosions and combustion is
No, but can you complete this graph that you just made now?
yeah, so let me just finish with the exothermic. So combustion is also an exothermic reaction because it gives out more energy. Example for endothermic is photosynthesis, and I'm also going to write a reaction down. So that is the nitrogen and oxygen reaction, which is also mentioned in your book. So let me just write the chemical formula. Okay. So don't forget writing the state symbols. Okay. Okay. So if I draw them out, this is how it's going to be. And can you notice that nitrogen needs 3 more electrons to complete its octet, right? And oxygen needs 2 more. But if you look over here, the oxygen is getting, it's completing its octet, but the nitrogen isn't. So there is going to be some charge on that, and that makes them less stable. That makes them even more reactive. So they have less stability. That means they're more reactive. Okay, so uh, reactions are all about molecules trying to get stable, right? So they just transferred from a more stable, you could say, level to a less stable level. So they're obviously going to be like mad about it. So they are going to be like more reactive. Okay, and it even has a charge on it, so kind of like an ion. Okay, and it's a pollutant gas. Okay, so it's lucky that this reaction needs so much activation energy. Okay, so basically exothermic reactions are more likely to happen than endothermic reactions. So this is because exothermic reactions need less activation energy, so even a small amount of energy is going to set the reaction off. Okay, that's why houses catch on fire by a small spark. You just need that one activation energy, and the rest of the reaction is going to happen automatically. Okay, but endothermic reactions, you need to give them energy. So
You know why is fire such an exothermic reaction? This is a very important concept. We
so
should all
uh
know this.
so I'm going to move on to that and
Okay. Okay.
later on. Okay, so uh yeah, so exothermic reactions need to take in less energy than they take out. Okay, so think of fire whenever you think of exothermic reactions, and endothermic reaction, think of baking a cake. So we mix everything in the batter and then we put it in the oven. So we need to give it a fixed amount of energy, and then it's going to turn into a cake, right? So the cake is not very reactive, but the substances that made it were, because they can go bad. Cake is not that likely to go bad. So, so just think of exothermic reaction as fire and endothermic reaction as baking a cake. Okay, so and the exothermic reactions are easier. Okay, now I want to talk about entropy. So entropy is
But
more.
you didn't explain. You didn't explain why
So
fire was such
I'll
an
get on
exothermic
to
reaction.
that after entropy.
Okay. Okay.
Okay, so entropy is a more difficult concept to grasp. Okay, so it's a chemical's randomness, and that's kind of confusing. Okay, so I'll try to help you understand. Okay, so think of a giant pile of golf balls. Okay, so I'm not drawing all of them. So there's a stack of golf balls. Okay, so they're all stacked up, okay, in an ordered fashion. Okay, so because they're ordered, that means they have low entropy. But then imagine a person comes along and then, knocks them all out. So they're gonna start bouncing everywhere, and some of them are gonna bounce so high they're gonna move up this hill and then down into the product hole. right? So the products are going to be formed, right? So this is entropy. So there were any any molecule which got um, that activation energy managed to become a product, but whichever couldn't just stayed the way it did. So it was all about like chance, okay? So by chance. So you can this is what so entropy is everywhere. Entropy is a very large topic, and it's kind of difficult to understand because we are used to chemicals following a law, right? But this is just randomness. But even entropy, so entropy is in every chemical reaction, okay? But there are many other factors many other factors affecting the reaction. So there could be temperature, there could be pressure, and all of that decides how many of the reactions are going to end up being products. So think of a closed container, okay? And we have all our reactants filled in it, and we start increasing its temperature. So any two reactant molecules which collide with enough force to become a product are going to be the only ones, undergoing that reaction. So it was entropy. So it it was just by chance that those two molecules got enough energy, and their collision was successful. Okay, so entropy is basically um, a chemical's randomness, right? But that definition is kind of correct and also kind of wrong. Okay, so if I asked you which of these two glasses were more random, which substance in these two glasses was more random, most of the people are going to say the ice. But that's not the case. The liquid has higher entropy. So this has lower entropy, and this has higher entropy. And I'll tell you how. Okay? So first of all, I want you to think of entropy as probability, okay? And I'm going to be using this diagram. Just give me a second. I'll be right back.
So entropy, is that energy within a system which is not used to do useful work. I mean, it is entrapped within the substances. It is entrapped within the substances. But because, work in terms of substances is done by the ordered motion of the molecules, okay? And because this, as she's saying, it is the level of randomness. So yeah, Sundus,
Yeah.
is entropy included in IDCSE syllabus?
I checked, and it was they said that it was better to know it.
Okay.
Okay. So I want you to think of solid A and solid B. Okay, so they have 6 chemical bonds each, and I told you that each chemical bond has energy, right? So I'm going to talk about units of energy. So I'm going to be calling them coulombs, okay, or quantum.
Can you please keep things simple, okay, Sundus? Keep
Yeah,
things simple.
yeah. So that's just a fancy word. It's pretty easy to understand. Um, so basically, think of
Okay. If any of the participants do not understand, you can raise your hand and ask your questions. Okay, you're welcome to do that.
okay. So each of these particles,
Only 15 minutes are left.
okay, so each of these particles have energy in their bonds. Okay, so solid A has more energy, okay, as you can see, than solid B, right? So now imagine, so energy is never static. So all of these quantums of energy are going to start, moving around. And for these two molecules, so first of all, you need to know what a microstate is, okay? So so this is a microstate. Microstate is the state in which the energy is. So this is one microstate, and if I move this energy over, this energy quantum here, this is another microstate, this is yet another microstate. So basically the different types of arrangements there can be out of all the quantums of energy. Okay, so these two molecules alone have 9,702 microstates. Okay, 9,702 different ways in which these quantums of energy can be arranged. Okay, so this energy keeps moving from its neighboring bonds, so they're constantly in motion, and so there's also chance that this energy is gonna jump from this substance to this one, right?
Okay, Sundus,
So
Sundus, I think we should start this in the next class. Okay, why don't you go back to that graph that you made? You know, the graph that you made for the endothermic reaction in which the products were at a higher energy level than the reactants.
yeah,
Yeah, can I have that graph back?
okay, sure,
Yeah, we'll start this in the next class.
okay.
Yeah, because this is too complicated.
Just give me a second. Are you talking about this graph?
Yes, yes. So now tell me what will be the energy absorbed in this case. With the help of a different colored marker, show us with the help of arrow the energy which will be absorbed by this particular reaction.
This will be the energy absorbed, and this will be the energy given out.
Yes, from the top till P, right?
Yeah,
Till the P.
yeah,
Yes.
yeah.
Okay. So what is the net energy absorbed?
So the net energy absorbed is the difference
Yeah,
between
between the product and the
the
reactant.
levels of the reactant and the product.
So that is usually the net reaction, which is released in the case of exothermic reactions and absorbed in the case of endothermic reactions. So in endothermic reactions, the products are at a higher level compared to reactants. And in exothermic, products are at a lower level than the reactants. And now, because you know we are running out of time, so let's talk about fire being an exothermic reaction.
Okay, so I actually prepared for that. Let me just take the page out. Okay, so over here I have the combustion
Yeah,
of
very good.
methane with oxygens giving us carbon
This is
dioxide.
methanol. This is
Uh,
methanol.
oh, okay. Okay,
Yeah,
yeah.
because
So sorry. I'm so sorry. Yeah, yeah.
yeah, whenever there's OH in a hydrocarbon, its suffix would be all. It's an
Yeah.
alcohol. Yeah,
I
belongs to
was
the alcohol family.
I
Okay.
was mistaking it for the reaction in the book. Okay. So this is methanol reacting with oxygen, giving us carbon dioxide and water. So I have drawn out all of these, drawn out all of the molecules. Okay. And in a question like this, they're going to give you the bond energies. Okay. So basically what we're trying to prove over here is that that combustion is an exothermic reaction, which means the energy taken in is less than the energy given out. So uh, we're gonna count all the different types of bonds and we're gonna write them down, right? So let's talk about the CH. So we have 3 CH bonds, okay, over here, but then we have 2 of the whole molecule, so we have 6 CH bonds. Okay, so if anyone doesn't understand, just stop me. Okay, so
Another thing, correct the formula for oxygen.
oh, I'm so sorry. Yeah.
Yeah.
Okay.
Okay. Just a little thing that I want to add here before we go into these details. Remember, carbon and oxygen, they love each other. They want to be together. Okay. They want to be together. You give them an opportunity and they will bond together. Carbon dioxide. Why? Because carbon dioxide is a very, very stable molecule, one of the stablest molecules on Earth. And so that is why it is very important to keep them apart if you don't want that reaction taking place. That's why the moment the fuel is exposed to the air, and if it's hot enough, and if the temperature is hot enough to provide the required activation energy, boom, there will be a reaction and fire. That's why we say these are explosive, So hydrocarbon fuels, they have to be covered if you don't want fire. Okay, and that is why this is such an exothermic reaction, because the moment carbon and oxygen form this bond and this molecule is formed, lots and lots of energy is released, and so the reaction gets highly exothermic, so much so that we use hydrocarbons as fuels. Okay, so that is one reason why fire is such an exothermic reaction, is because carbon dioxide molecule is very stable. So nature is trying to, carbon and oxygen want to bond together. Okay, so yes, Sundus, go ahead with your calculation.
Okay, so CH has a bond of 412, right? So, and I'm going to multiply that by 6 because we're going to have 6 of these, okay? And then I'm going to add that with this bond, so that's 360, and we have 2 of them. So 360 multiplied by 2, okay? And then we have hydrogen and oxygen. So we
Look
have
at the bond energies. Look at the bond energies. Which bond has the most energy? Carbon oxygen double bond. Can you see that? So that's the amount of energy that will be released by one carbon atom making double bonds with one oxygen atom. So just imagine what the total energy released would be, because we will have a lot of carbon dioxide molecules being formed. Okay.
so after that we have oxygen and hydrogen bond. Again, 2 of these, okay? So 2 multiplied by 464, okay? And then we're going to add it with oxygen double bond, but we have 3 of them, so that's these. We're going to just 498 multiplied by 3, okay? And then we're going to calculate this and compare it with the product, right? So let me just get the calculator.
Okay.
Okay, so in a question like this, don't go too fast, okay, and just do the smaller additions first so that you don't mix them up, okay? So I'm going to write each of these like this, okay? And so this is 9, 8, 9. This is 1494, 2, 4, 7, 2 plus 720 plus. So we have 5,614 kilojoules per mole of energy taken in. And now we're going to do the same thing for the product. Okay?
So now we will calculate the energy released. So this is the energy required.
Taken in.
Okay. Yes.
So now we have
this is the energy required to get to that peak of the graph.
Exactly.
From the reactants to the peak of the graph. And also show them that at the peak you have individual atoms, meaning all the bonds have been broken and atoms have and atoms have separated from each other, so they no longer exist in the molecular form, but they are in separate atomic forms. Okay.
Yeah.
Now
So,
the energy released.
so I have oxygen carbon double bond. I have 2 of them, and then I have 2 of the whole molecule, so that makes it 4, right? Because if I remove that, this is what it means. So I have 4 of these bonds. So I'm going to write 805 multiplied by 4 and add that with,
Yeah, do you have okay.
okay, hydrogen and oxygen bond is 464, and I have 2 of them and then 4 over here. So I'm going to multiply it by 8. Okay, so I have 464 multiplied by 8, and that gives me, so first I'm going to do I'm going to solve the brackets. So 3220,
I think it's 6932.
so yeah, it's 6932 kilojoules per mole. So
I think they use negative for the energy released and positive for the energy absorbed.
yeah, so the energy taken in was of less than the energy given out. So that's why. So this is an exothermic reaction.
So what is the net energy released?
So the net energy release will be the difference between the energy taken in and the energy given out. So I'm just going to take one away from the other, and that gives me 1,318 kilojoules per mole net.
So this is the difference between the two, okay, ignoring their signs.
Yeah.
And what sign will you put? Is this an energy released or energy absorbed? So the final answer will have that sign.
Yeah, so this is
released,
the energy
right?
released. So
Yeah. Or another way of looking at it is just add them along with their signs.
yeah,
Okay?
exactly.
Add them along with their signs, and the sign of the final answer would be the sign of the bigger number.
Yeah.
Just
So
like as you have in algebra, in math.
so the sign of the larger number is going to be the sign of the answer.
Okay, now if there's any question, please feel free to ask. Absolutely any question at all. Don't think that your question would be silly, or it's open. Sometimes silly questions are the ones from which we learn, that we think are silly. Yes?
Anyone? Okay, Sarah.
Yes.
Miss, what is quantum energy?
Yeah, I that's why I stopped, Sundus. I don't want you guys to get into that as yet. We will discuss that later. Okay. Is there any other question other than that? Okay. So if there is no question, then I think we will end here. Then inshallah, day after tomorrow, we will have physics class.
Okay.
Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.
Allah Hafiz.
You're most welcome. Assalamu alaikum.
Allah Hafiz, everyone.